Okay, so we're going to find the least square regression line and use it to make predictions and interpret the slope of the y-intercept of the least square regression lines, and then compute the sum of squared residuals. Um, just some things to note. We're going to use a calculator to do most of this, so some of these formulas may not be useful to you for now. But we have what's called the point slope formula. Y1 and X1 and M. So M is the slope, X1 and Y1 is the point. Oops. And so you can use those to calculate the formula for this equation if you're given data in this type of format. And so I'm kind of curious why they use 2 and 5.7 when they have a 0 there, but that's fine. They can do whatever they want. So they calculate the slope. That's your M. Plug these values into this, and then they can kind of solve for the equation of the line, and it has a negative correlation in this case. So if you look at the graph, there's a best fitting line. It's the one that goes between those points. It doesn't necessarily have to touch all of them, but it should fit between them somehow. Use the equation to predict y if x is 3. Well, if you go to x is 3, that would be up here. You'd say that that's roughly 5-ish. Almost 5, 4.75 is what they actually calculated it to using the equation. The difference between the observed value of y and the predicted value of y is the error or residual. Using the lines from the last example and the predicted value at x equals 3, residual is equal to the observed y minus the predicted y. So the observed y is 5.2, the predicted should be 4.75, so that's 0.45 in total, distance between them. So the least square regression line is the line that minimizes the sum of the squared errors or residuals. This line minimizes the sum of the squared vertical distance between the observed values and the y and the predicted values, y hat. We represent this as minimal sum residual squared. Minimize sum residuals squared. So the equation of the least square regression line is given by y hat is equal to b1x plus b0, b naught. And so b1 is r times sy, the standard deviation of y over the standard deviation of x, where b naught is y bar minus b1 times x bar is the y-intercept of the least squares regression line. X bar is the mean, y bar is the mean of the y's, and so you'd have to do the mean of both of those to figure this out, but we're using a calculator, don't forget. Find the least square regression line. Predict the time drilling if it starts at 130 feet. Is the observed data drilling time at 130 feet above or below the average? And then draw the squares regression line on the scatter plot of the determined data. We agreed around the estimates of the slope and interpret to 4 decimal places. So we've been doing that anyway. They calculated y hat is this. They plug in 130 to figure out part B, and then obviously they used a calculator to get that because they used the data from right here. Okay, and so they plugged in 130 and they find that at 7.035. The observed drilling data is 6.93 seconds. The predicted value is 7.035. So the drilling time is below average. So it kind of went a little bit quicker. That would be this point here. And then interpretation of the slope. Slope of the regression line is 0.0116 for each individual or additional foot. The depth that we start drilling, the time to drill 5 feet increases by 0.0116 minutes on average. The y-intercept of the regression line is 5.5273. To interpret the y-intercept, we must first ask 2 questions. 0 a reasonable value for the explanatory variable, and do any observations near x is equal to 0 exist in the data set. A value of 0 is reasonable for the drilling data. This indicates the drilling begins at the surface of the Earth. The smallest observation in the dataset is at x is equal to 35 feet, which is reasonably close to 0, so the interpretation of y-intercept is reasonable. The time to drill 5 feet when we begin drilling at the surface is 5.5273 minutes. Okay. So a caution, if the least square regression line is to be used to make predictions based on the values of the explanatory variable that are much larger or much smaller than the observed values, we say the researcher is working outside of the scope of the model. Never use the least square regression line to make predictions outside of the scope of the model because we can't be sure the linear relation continues to exist. So it might only exist within a small frame. It might vary. If, for instance, you asked the distance if you drilled something that was bigger than maybe the Earth's surface or something. So back to the drilling, maybe it's outside of our capabilities to drill more than 2,500 feet in the ground or something like that, and you're asking for 40 million feet in the ground. So to illustrate the fact that the sum of the squared residuals for a least squared regression line is less than the sum of the square residuals for any other line, use the regression by eye applet. And so that is that for this. I'll do a video to show you kind of how to use the calculator to do these things. And that will be that for this section. Thank you guys for watching.